traveled 7 hours, drove 7 hours to be here with us, so we really very much appreciate that. His co-author is Ted Oyama, and this is a contribution from Virginia Polytech. And the title of his talk is A Study on the Ozone Decomposition Activity of Supported Manganese Oxides. Rakesh?
Thank you for the introduction. I don't know how many of you know the research activities which go on at Virginia Tech, but it's mostly polymer area research and bio research. So I'm actually pretty happy that I'm sitting in a conference where I can actually hear something about catalysis, because most of the people who are brought in are all polymer lecturers or bio lecturers. So the topic of my talk for today is a study on the ozone decomposition activity of supported manganese oxides. This work was done as part of my PhD work with Dr. Ted Oyama, who's heading up the Environmental Catalysis and Materials Lab at Virginia Tech University. The work was done in collaboration with Dr. Kiyotaka Asakura of Hokkaido University in Japan and Dr. Jinghua Chen, who is at the University of Delaware right now. Let me start out by giving you an outline for today's talk. I'm going to begin with background information, and here I'm going to discuss why we're interested in studying ozone decomposition, and I'm also going to provide some details about the thermodynamics of the ozone decomposition reaction. This is then going to lead me into the preparation and characterization of manganese oxide catalysts for the ozone decomposition process. And finally, I'm going to show you the kinetic analysis which I used to evaluate the effect of support on the catalyst activity. In terms of the background information, why we are interested in studying ozone decomposition? Well, at ground level, ozone is a pollutant, and it's typically released from copiers, printers, purification units, which are essentially used for purifying water, and also some sterilization equipment. The health effects of ozone is that between concentrations of 0.1 and 1 ppm, it generally leads to headaches, damages mucous membranes, causes breathing problems, and also causes throat dryness. Because of these health effects, OSHA has set a standard threshold level to exposure for ozone for an 8-hour period of 0.08 ppm. The ozone decomposition reaction itself thermodynamically is favored. It's an exothermic reaction. And the main product of the ozone decomposition reaction, actually the only product, is gas phase oxygen. However, ozone is very stable, and it's in fact stable up to 523 Kelvin. And to illustrate the stability, just to give you an idea, a half-life of a 1 mole % ozone-oxygen mixture at room temperature, assuming there's no convection or anything like that, is 19.3 years. There has been a lot of patent literature, and some of you might be wondering why we're still interested in studying manganese oxide, because patent literature has pretty much identified manganese oxide as a very good catalyst for the reaction. However, there is a lacking in the fundamental understanding of the ozone decomposition mechanism and what the effect of support is on the manganese oxide activity, which is why we selected manganese oxide as the catalyst for these studies. The catalysts itself were prepared using a 3-weight% manganese oxide basis, and they were supported on supports of alumina, silica, titania, and zirconia. The alumina, titania, and zirconia samples were obtained from Degussa Corporation, and the silica sample was obtained from the Cavasil Corporation. The precursor for the manganese oxide manufacture process was manganese acetate tetrahydrate, which was obtained from Aldrich Corporation, 99.9% purity. The technique for manufacture of the catalyst was the incipient wetness technique, and typically we just use the precursor solution, which was dissolved in a fixed amount of the distilled water and impregnated onto the sample. Once the sample was impregnated, we heated it at 393 Kelvin for 6 hours and calcined it at 773 K for 6 hours. The catalysts were characterized using Raman spectroscopy, essentially to evaluate the type of manganese oxide species we had on the surface. Extended X-ray absorption fine structure work was done in Japan to try and evaluate the local coordination of the manganese site. Near-edge X-ray absorption fine structure was used to try and determine what oxidation state the manganese is in. This was also used to try and evaluate what the effect of support was on the oxidation state of the manganese. Temperature programmed oxygen desorption was then used to estimate the number of active sites we had on the surface of the catalyst. And finally, we used surface area measurements using a micromeritics unit and using nitrogen physisorption. I now present here the Raman spectra we obtained for the 4 catalysts. And it's important that I mention here that before we acquired the Raman spectra, which were acquired in situ, the catalysts were pre-treated in oxygen flow at 773 Kelvin for 2 hours. The actual spectra were acquired in situ during actual oxygen flow at ambient conditions. And what we essentially see in the case of zirconia are peaks at 638, 618, and 552. And then there are a couple of peaks in the lower wave number region as well. These are all support peaks. In the case of the titania, the peak at 632, and then there's something around 400, which is also a support peak. In the case of both the alumina and the silica, the supports really didn't have any strong features in the regime we are showing right here. However, with the introduction of manganese, essentially what we see is for the alumina, the appearance of a feature at 661, and for the silica, an appearance of a feature at 664. We have realized that from our XAFS work as well, that the species on the surface of the alumina is a manganese surrounded by 5 oxygen atoms, and that this frequency essentially is the manganese oxygen stretching frequency. In the case of the alumina sample, what we've seen from XAFS work, which I'm going to present in the next slide, is that it's a manganese species surrounded by 5 oxygen atoms. However, in the case of both the titania and the silica, what we essentially see is that it's a multinuclear manganese species with the oxygen coordination still remaining the same as the previous. That's a 5 coordination. Now I present the XAFS spectra. This was again acquired by Dr. Asakura in Japan, and he has a lot of the information with him because this is still an ongoing work. What he essentially looked at was comparing the manganese on alumina, titania, and silica to a couple of commonly occurring manganese oxides, gamma manganese oxide, beta manganese oxide, and Mn3O4. The reason why I don't have the zirconia here is because of interference from the zirconia support itself. We were not able to acquire similar data for the zirconia. What we essentially see are 3 features from this plot. There's a feature at about 2.0 angstroms, and this has been identified that from the manganese to oxygen. And essentially, when we quantify the fitting procedure, what we get is an n equals 5, which is how we got the local coordination of the manganese site. The peaks at 2.7 and about 3.1 are both manganese to manganese nearest neighbor contributions. And what we essentially see is that in the case of titania and silica, those are very pronounced features, which is why we concluded that these are likely multinuclear species with manganese, whereas the alumina is likely just a mononuclear species. We then looked at the near-edge X-ray absorption fine structure spectra, and this work was done by Dr. Jingguan Chen while he was still at Brookhaven National Labs. And he looked at the manganese L-edge feature. And essentially what this gives us is information about the oxidation state, or at least it should have. What happened here was we needed to take the ratio of the L-edge features, the L2 feature and the L3 feature, and the ratio of the L3 over L2 peaks essentially gives us a relative oxidation state. What we essentially saw was that all of these catalysts were in mixed oxidation states, but the manganese on alumina and the manganese on zirconia were closer to a +2 oxidation state, whereas the titania and silica were closer to a +4 oxidation state. Additionally, there is also a shift in these features which follows the trend alumina, zirconia, titania, and silica. We kept this in mind while we were doing all of our other work as well. And what we essentially did next was we tried to look at temperature programmed desorption technique to try and estimate the number of active sites we had on the catalyst. This was a very important thing because essentially what we found was a traditional oxygen chemisorption technique which we've used in the past with molybdenum oxide catalysts did not really work for the manganese on alumina or any of the other catalysts either. The reason for this we're still wondering about, but the main thing was that what we essentially saw was the same amount, we were getting an extremely low amount of oxygen uptake, which is why we decided to go with the temperature programmed desorption route of an actual reactant probe. And what I have essentially presented here is an example for the manganese on alumina catalyst. What we essentially do here is we pre-treat the sample again in oxygen flow at 773 K for 2 hours. Then we introduce ozone onto the sample at a very low temperature, 233 Kelvin. This adsorption process is done for about 2 hours. And then we gradually monitor the desorption trace for the mass to signal ratio of 32, which corresponds to oxygen. What we essentially see here is a peak at 410 Kelvin, and earlier work done in our lab has identified that peak to be an adsorbed peroxide species peak, as basically a dissolving O2 species. In the case of the 537 Kelvin peak, again, previous work has identified this as a peak resulting from a recombination of an atomic oxygen species followed by a desorption. The peaks at 835 and 1095 Kelvin are bulk reduction peaks. And how we know this is that when we look at the manganese on alumina sample without any ozone adsorbed, we essentially see those peaks in the TPD trace. And we know that this is the feature from bulk manganese oxide reduction because when we look at the alumina for both the ozone adsorbed and no ozone adsorbed, we do not see any features. Well, similar experiments were performed for all of the other catalysts, and you're wondering how we estimated the actual amount of active sites from these plots. Well, essentially what we see are features at 410 and 537 pretty much for all of the catalysts. And an interesting feature in the case of the zirconia is that we actually see two different peroxide species peaks, one at 370 Kelvin and another at 410 Kelvin. In fact, we were able to observe this using in situ Raman spectroscopy as well, which I'll present a little later on. What we do after these traces are taken is essentially we cool the sample down to room temperature, and then we pulse a known amount of oxygen. And basically by quantifying the area under the peak, we are able to identify how much oxygen has been pulsed, and then we quantify the areas under these peaks based upon that calibration. And this gives us an estimate of the site density for our supported catalyst samples. And here's where I present those results. What we essentially see is that for the alumina catalyst, it's about 40. And we generally see a trend, it's the lowest for the silica sample, about 13. The reason why it's so high for the zirconia is because, again, we had two features there. And I'm going to talk a little bit more about this later. The surface areas for the catalyst pretty much did not change from the actual supports. It's about 90 for the traditional aluminas which we used. It's about 90 for the silica, and it's about 50 for the zirconia and titanium for the samples we used. Now I want to talk about the reaction kinetics we used to try and evaluate the effect of support. Earlier work done by Dr. Whaley in our lab has identified an ozone decomposition mechanism, and he did this using some isotopic work and a little bit of ab initio calculation work as well. And what he essentially saw was that the adsorption procedure proceeds with an ozone molecule essentially depositing on an active center to produce an adsorbed atomic oxygen species. This adsorbed atomic oxygen species then recombines with an ozone molecule to give us an adsorbed peroxide species. The adsorbed peroxide species then dissolves, giving us gas phase oxygen. Essentially, using this kinetic analysis, basically for the mechanism, we were then able to look at a kinetic analysis which incorporated the surface coverage of the peroxide species. This was a non-uniform kinetic analysis, and the surface coverage was estimated using in situ laser Raman spectroscopy while during actual reaction conditions. And what we essentially did here was that we used an adsorption rate, which was a function of ozone partial pressure and coverage, and a desorption rate, which is a function of the coverage alone. When we set the two equal at steady state, what we essentially see is an expression for the steady state coverage, which depends upon the Bronsted parameters G and H and ozone partial pressure. When we plug this expression back into either of these desorption rate or adsorption rate expressions, what we are able to observe is a steady state reaction rate, which depends upon ozone partial pressure. An interesting feature about this proposed kinetic mechanism and analysis is that it predicts a fractional order H over G plus H for the ozone partial pressure dependency. Essentially, these two expressions can then be used with a complementary experimental data to estimate both the Bronsted parameters G and H and the reaction rate constants Ka0 and Kd0. And how we do this is essentially we use the turnover rates based upon the number of active sites we estimated using oxygen TPD. We then monitor the reaction rates using an in situ laser Raman spectroscopy system, and we monitor these rates as functions of temperature and ozone partial pressure. And we also monitor the steady state coverage as a function of temperature and ozone partial pressure. The experimental conditions we used essentially was this system was at 1 atmosphere pressure and the reactor volume was about 10 cc's. We used a flow rate of ozone-oxygen mixture of about 1,000 cc's a minute, and the catalyst mass was 0.3 grams. The catalyst itself was a thin cylindrical wafer of 1.5 centimeter outer diameter and 0.1 centimeter thickness. And before we run the reaction, we pre-treat the sample in oxygen flow for 2 hours at 773 Kelvin, just like the other procedures. And then we look at a temperature range between 293 Kelvin and 343 Kelvin, and a partial pressure range for ozone between 600 and 3,000 pascals. These studies were conducted using an in situ laser Raman system, and here's a schematic of the system. Essentially what we use is an ozone generator which operates on the corona discharge principle. What we do is we feed a stream of oxygen into the ozone generator, and it gives us an ozone-oxygen mixture which we are able to feed directly onto the sample. The sample itself is rotated at about 1500 RPMs to prevent local heating from the argon-ion laser. The scattered light from the sample is then collected through a notch filter and a focusing lens into a monochromator which is equipped with a CCD detector. And this system is set up so that it can acquire the data using a computer data acquisition system. The outlet gases are analyzed using an ozone analyzer which essentially works in the UV absorption tools. Now I present here an example of some of the data which we obtained and how we analyzed it. Here I present the manganese on zirconia because if you recall from my TPD spectra, I observed 2 different peroxide species peaks, at least that's what we think it is. When we look at the manganese on zirconia right after catalyst, right after pre-treatment of the catalyst, we essentially observe a bunch of peaks between 638 and 342 wave numbers. All of these peaks are support peaks. And this is done in oxygen flow. As soon as we introduce ozone, what we essentially see is the appearance of a peak at 880, another peak at 852, and a third one at 930. The peaks at 852 and 880 are the peroxide species peaks, which I talked about earlier. The peak at 930 is a combination band. This is at room temperature, about 293 Kelvin. And essentially what we see is that as we increase the temperature, we see a gradual decrease of the area under these peaks and also the intensity. And what we are essentially able to do is quantify the area under these peaks, and we normalize it to the largest ozone partial pressure and the lowest temperature to obtain normalized coverages. And this is the data I present here, where we look at the coverage as a function of the ozone partial pressure. And what we essentially see is that with increasing ozone partial pressure, the coverage increases gradually, eventually reaching saturation. With increase in temperature, the coverage decreases, as you saw in those plots. The information we are able to extract from this is that the slope of the line, when we plot the theta versus the log here, is that it gives us a slope of 1 over G plus H. And G plus H, if you recall, are the Bronsted parameters. It also gives us a set of constants which we can use then with the complementary rate versus ozone partial pressure data. And this is what I show here next, is that with increasing ozone partial pressure, the ozone decomposition rate increases. And the ozone decomposition rate also increases with temperature. When we look at this data and we plot log rate versus log ozone partial pressure, we are able to extract the slope, H over G plus H. And then this gives us a set of constants KD0, involving KD0 and KA0, which we are able to use with the constants we got from the previous expression to evaluate both our pre-exponentials, AA zeros and AD zeros. and also our apparent activation energies for absorption and desorption. This is the data which I present here, and essentially I have three catalysts compared: the titanium, zirconia, and the alumina. When we look at the Bronsted parameters, there seems to be no particular trend there. Additionally, when we look at the absorption pre-exponential and the absorption activation energy, we see that there's a very low activation energy for absorption, and the absorption pre-exponential does not change substantially either. Well, the primary difference, it seems like, is coming from the desorption pre-exponential, which is about 100 times greater for the alumina compared to the zirconia, which is 100 times greater than the titanium. The activation energies for desorption were very high, which seems to indicate that that's why we were able to see the actual absorbed species peaks using in situ Raman spectroscopy. The work done on the alumina was done by Dr. Whaley and has been published in the Journal of American Chemical Society in 1998. We've then looked at the Arrhenius plots, and essentially we looked at the largest ozone partial pressure, and we looked at the activity as a function of the temperature. And what we essentially see is that in the case of the alumina, we get a very low apparent activation energy. And in fact, the trend follows alumina, zirconia, titania, silica, which I'm going to present next. And if you recall, I mentioned that the reaction order should be fractional. And what we pretty much see is that they're all fractional, 0.99 for the alumina. This might be closer to 1. However, in the case of zirconia, titania, and silica, they pretty much maintain the trend which we expected. When we look at the apparent activation energy, we see that the trend follows alumina, zirconia, titania, and silica. And if you recall from the Nexaf shift, the trend which we observed was alumina, zirconia, titania, and silica. So we think that the Nexaf is essentially giving us information about the desorption step. To conclude, essentially what we observed was that the reason why we were probably able to observe and use a non-uniform surface kinetic analysis like we did was probably because the manganese was in mixed oxidation states with different affinities for ozone decomposition. The primary difference in the activity was a result of the desorption kinetic parameters changing with support. The Nexaf shift for the catalyst followed the trend alumina, zirconia, titania, silica, which was the same trend observed for the apparent activation energies for the catalyst. At this time, I would like to thank the NSF for supporting this work, Dr. Whaley for some of the preliminary ozone decomposition work, and the Chemical Engineering Department at Virginia Tech for providing me with the laptop and the projector screen. Thank you.
Have time for some questions?
Yes.
Is there an actual bonding between manganese oxide and the supports, and what's the mode of bonding?
Yeah, that's an interesting question. We did this because there's been very little work done in terms of what type of bonding or what's the oxidation state of the manganese. What we think is happening is that it's in fact a manganese plus 4. If you recall, it's a 5-coordinate manganese species. So there are 4 oxygens which are being bonded to the support. The 5th oxygen is just something which is coming off the vacancy or something like that from the support itself. There's no actual bond. That's what I think it is right now. But we are still, in the process of consulting with Dr. Asakura about that.
Also, do you see any patterns on the XRD?
Oh yeah, the loadings at which we look at these, yeah, we don't see anything. That's why we used Raman and any other techniques we could.
The question?
Yeah. First of all, how much manganese, did I miss that someplace? How much manganese do you
3
have?
weight percent loading. Yeah.
And is that even too low for looking at?
Well, that's the thing. 3 weight percent is good enough to look at through Raman because a lot of molecularly dispersed species, and if you look at literature for molybdenum oxide and things like that, they've gone as low as 1 weight percent, and they've been able to observe that.
And then the other one was related to the decomposition.
Mhm.
Is the challenge really to be able to reduce that very low ppm, sub-ppm quantity to another order of magnitude lower?
Well, actually, the thing is that what's interesting about it is that when we look at just a blank reactor, and we have, it's a pretty low ppm anyway, but we pretty much get that out. But in the case of the manganese, as soon as we have any manganese there, it's reduced almost instantly, and the UV analyzer we use is also pretty good. What it gives us, it's between a range of 48 grams per meter cubed to 0, essentially. So we are able to observe the entire range.
Peter?
How's your activity as a function of temperature? I ask you because there's a company, Carlos Chemicals, who is actually providing these catalysts, and they have complete transformation at 25 Celsius. Who's this catalyst? Manganese and alumina.
Yeah, alumina, right? Yeah.
How's your activity as a function of?
Well, the thing is that this is not a commercial catalyst. We've just looked at powder catalysts. The next step would be to try and incorporate these studies onto actual commercial, type, essentially the type of corderite materials and things like that, and see what the activity trends are and see if that mirrors what we see here. We have not really tested it with a commercial although an earlier study done by Dr. Dandapani has actually looked at that, actually looked at some of the commercial catalysts and manganese oxide catalysts.
What I'm asking is, do you have activity, complete transformation at very low temperature?
Yeah, we have complete conversion at very low temperatures. Yeah.
Your activation energy seems to be too low for a chemical reaction. Have you ever wondered about that?
Well, the activation energy for desorption
for
or adsorption is...
Adsorption, you presented 5 kJ per mole, which is 2 kcal per mole.
Yes.
Which seems to indicate maybe it's a physical adsorption going on, or maybe there is some coverage effect in your kinetic data. Have you ever wondered?
Well, the thing whether it's physisorption or chemisorption. Now, the reason why I say it's chemisorption is because essentially your ozone dissociates to an O2 star, right?
Right.
So there must be some kind of chemical bonding. The ozone can't, necessarily, because if it was a physisorption, then wouldn't you expect the ozone just directly to go onto the sample?
Right. What you're saying is right, but that might also make your kinetic data suspicious in that coverage might affect the activation energies. So that, to me, it says that maybe you're going too much coverage on the surface. In a sense, you're not measuring initial rates to determine these kinetic parameters.
The only thing I can tell you is that this work was done just recently, and we are kind of limited by the equipment we have too. We essentially, the in situ Raman spectroscopy system, we limited to the ozone partial pressure range we have from the generator and the analysis we can do with the analyzer. So yes, one of the future works would have to be to go to a broader pressure range and see if that makes a difference or not, and if those kinetic parameters are truly what they seem like they are. But the initial encouragement about this is the fact that we are able to observe the peroxide species peak using Raman, which seems to indicate that the adsorption is almost instantaneous. As soon as we absorb, we use the ozone on the sample, it adsorbs and we see that peak instantly. So we don't have a pre-treatment period or anything like that. It's almost instant.
Ish, we thank you very much.
Thank you.